So we continue with the exercises. So we are at number 8. Let AB be a finite interval in R. Let phi n equals 1 to infinity, be an orthonormal basis for L2 of AB. Recall that L2 is a separable space, therefore it has a countable orthonormal basis. Then phi mn st equals phi n of S, so Nm if you like, to keep the same order. Phi m of t gives an orthonormal basis for L2 of AB cross AB. Okay, so solution. So let F belong to L2 of AB cross AB. Then what do we have? Integral A to B mod FST square ds dt is less than infinity. So then by Fubini's theorem, we have for almost every t, we have integral mod FST square ds is finite AB, and for almost every s, we have integral A to B mod FST square dt is finite. So this implies that for almost every t, S going to f of st belongs to L2 of AB, and similarly for almost every S, t going to f of st belongs to L2 of AB. So this is just direct application of Fubini's theorem. Okay. So let us consider mod phi nm square ds dt, and this is integral of AB or cross AB. Okay, so this is, since the functions are the variables are separated, so this just breaks up into two integrals, A to B mod phi n s square ds integral A to B phi m t square dt. Okay, and that is of course not only finite, but they are given to be each is equal to 1, and therefore this is equal to 1. Okay, so now let us consider the orthogonality. So integral of AB cross AB of phi ij phi kl ds dt. Okay, so then this will be equal to integral, again because of the variable separable nature, phi is phi ks ds, and integral A to B phi j t phi lt dt, and that will be equal to delta ik delta jl. Delta is the Kronecker symbol. This is equal to 1 if I equals, so delta ij or delta, let me say, pq equals 1 if p equals q, 0 if p is not equal to q. Okay, this is the Kronecker symbol, and therefore unless ij equal to KL, this will always be 0. Even if one of them is different, one of the two indices is different, this will be equal to 0, and therefore this shows that phi ij, 1 ij going from 1 to infinity is an orthonormal set. So now we have to show that it is complete. So let f belong to L2 of AB cross AB such that integral of AB cross AB of f of st phi ij of st ds dt equal to 0 for all ij. Okay, so then we have to show, to show f is equal to 0 almost everywhere, of course, that means it's 0 in the L2 sense. Okay. So let us take integral a to b mod integral a to b f of st phi it dt square ds. This is less than or equal to, by the Cauchy-Schwarz inequality, integral a to b. So this is mod fst square dt, and then integral a to b mod phi it square dt, and then the whole thing integral a to b ds. Okay, now this is given to be equal to 1 because we know it's an orthonormal sequence or basis in the thing. So this is less than or equal to integral a to b f of st mod f of st square dt ds, and that we know is finite. Therefore, this implies that s going to integral a to b f of st phi it dt belongs to L2 of AB for, okay, so that almost, okay, so this, because that's what we have shown. Okay, so we have shown that that integral is in L2 of AB. Okay, so now we have 0 equals integral AB cross AB f of st phi it phi js dt ds is equal to integral a to b of integral a to b, because now we can apply Fubini because modulus is all integrable and therefore there is no problem at all. Integral a to b f of st phi it dt into phi is ds, okay, phi js, sorry. Now this is given to be an L2 function and its inner product with every phi j is 0. So this implies that integral a to b f of st phi it dt equal to 0 for all I, and this implies that f of st equal to 0 almost everywhere, once again because s going to phi f st this is in L2. Okay, so that each of these is in L2, and therefore from these statements you get that f of st has to be 0 almost everywhere. Okay, so this implies that f equal to 0, and therefore we have completeness of the orthonormal basis. So remark, for instance, we saw that root of 2 by pi sin nt n in n was an orthonormal basis for L2 of 0 pi. So we have the 2 by pi sin nt sin ms is nm in n is an orthonormal basis for 0 pi L2 0 pi cross 0. Okay, so this gives you orthonormal basis for that. Okay, so 9, show that one by root pi union root of 2 by pi cos nt n equals 1 to infinity is an orthonormal basis for L2 0 pi. So this is the corresponding theorem. We saw that root 2 sin n pi t is an orthonormal basis. Now we are showing that this. So the proof. So you take f orthogonal to E, that means f is orthogonal to every member of these things. That means integral f times any of this is 0. Now extend f as an E, so f in L2 of 0 pi. An even function to minus pi pi. So for t positive, you have f of minus t is equal to f of t. So that's what you define. Then you have that f, now this extension belongs to minus pi pi. So if you now take, so you are given that f dt 1 by root pi equal to 0, and you are given that an and you are given that integral ft cos nt dt is also 0, 0 to pi, and this implies that integral minus pi to pi f dt, which is twice integral 0 to pi f dt, equal to 0, and similarly integral minus pi to pi of ft cos nt, because both are even functions now, this is equal to twice integral 0 to pi ft cos nt dt, and that's equal to 0. And then you have integral minus pi to pi ft sin nt dt, that is, this is even and this is odd, so the product is odd and therefore the integral is 0. So a naught, an, bn are all 0 for all n, and therefore you have that f is 0 on minus pi pi almost everywhere. Of course, this implies f is 0 almost everywhere on 0 pi, and therefore f is the 0 element of L2. Consequently, this is a complete orthonormal basis, complete orthonormal set or an orthonormal basis. So you can write a Fourier series corresponding to this. You can expand any L2 function in 0 pi in terms of the constant and the cosines, and that's called the Fourier cosine series, just as we had the Fourier sine series. 10. So fg in L2 minus pi pi, and ft is a naught by 2 plus sigma n equals 1 to infinity an cos nt plus bn sin nt, and gt equals c naught by 2 plus sigma n equals 1 to infinity cn cos nt plus dn sin nt. Okay, then show that 1 by pi integral minus pi to pi fg dt is nothing but a naught c naught by 2 plus sigma n equals 1 to infinity a n c n plus b n d n. Okay, so solution. So you take fn equals a naught by 2 plus sigma n equals 1 to capital N a n cos n t plus b n sin n t, and gn is c naught by 2 plus sigma n equals 1 to capital N cn cos n t plus dn sin n t. Okay, so then you have fn converges to f in L2 minus pi pi, and f capital N, sorry, and g capital N converges to g in L2 minus pi pi. And if you compute minus pi to pi fn gn dt, this is equal to a naught c naught by 4 into 2 pi, okay, plus sigma. You can just directly calculate this. So n equals 1 to n, okay. So you get integral minus pi to pi, okay, an cn cos square n t plus bn dn sin square n t. All the other cross terms will vanish because integral cos n t sin n t is 0 over minus pi pi. Which is pi times a naught c naught by 2 plus in sigma n equals 1 to capital N of integral minus pi to pi a n c n of 1 plus cos 2 n t by 2 plus b n dn into 1 plus 1 minus cos 2 n t by 2 and the whole thing dt. So cosine will become sine, and minus pi to pi, that will give you 0. So you get a n c n by 2 plus b n dn by 2 into 2 pi. So that will be pi times a naught c naught by 2 plus sigma n equals 1 to n a n c n plus b n dn. And now you let n tend to infinity. So on both sides, here you will get integral fg, here you will get sigma n equals 1 to infinity. Okay, so that will prove the theorem. That will give you the solution. Okay, so 11. So find the Fourier series for ft equal t. And for ft equals mod t. Use them to evaluate. So this is a standard exercise in Fourier series. Zeta 2 equals sigma 1 over n square, n equals 1 to infinity, and zeta 4 equals sigma n equals 1 to infinity 1 by n power 4. Okay, so solution. So ft equals t is an odd function on minus pi pi. So this means that all the ANs are 0. Okay, and Bn equals 1 by pi integral minus pi to pi t sine nt dt, and you do an integration by parts. So this you should work this out. So this will give you 2 by n minus 1 to the n plus 1. So integration by parts. Okay, so that I won't do it. Okay, so now 1 by pi, what is the Parseval identity? 1 by pi integral minus pi to pi t square dt is equal to sigma n a naught squared by 2 plus sigma n equals 1 to infinity an square plus bn square. Okay, so we have that 1 by pi t square is t cube by 3, so this is twice integral 0 to pi, so 2 by pi integral 0 to pi, and then you get t cube by 3, so that will give you pi cube by 3. So that will be equal to a naught is 0, all the n's are 0, so 4 times, what is that is 4 times mod minus 1 will become 1 when you this thing, sigma n equals 1 to infinity 1 by n square. Therefore this implies that zeta 2, which is sigma n equals 1 to infinity 1 by n square, is nothing but, if you take this to that side, you get pi square over 6. Okay. Now ft equals mod t is an even function over minus pi pi, and therefore this implies all the bn's are 0. Okay. And therefore a naught is equal to 1 by pi integral minus pi to pi mod t dt, which is equal to 2 by pi integral t dt 0 to pi, I don't have to put the mod, and that's equal to pi squared by t squared by, so this will just give me pi. Okay, an is equal to, again because it's a even function, this is 0 to pi t cos nt dt, again do the integration by parts, so this will give you 2 by pi n square into minus 1 power n minus 1. So again integration by parts. So you can check these calculations, this is a routine calculation. So you have that an is 0 if n is even, and an equal to minus, so this is n is odd, this will give you minus 2, so there will be minus 4 by pi n square if n is odd. Okay, so only the odd an's are surviving, all the rest are 0. So 1 by pi integral mod t square dt minus pi to pi, so that's equal to 2 by 3 pi square again. Same as before, because mod t square or t square is nothing. So okay, so 2 by 3 pi square, because 2 by 3 pi into pi cube by 3 is the same value as this. We have already done this calculation, no point doing it again. So that's just 2 by 3 pi square. Okay, and that's equal to a naught square by 2 plus sigma n equals 1 to infinity an square, and that's going to give you pi square, because what was a naught? Oh sorry, this Okay, pi square. Sorry, this is not n, it's n. Okay, so pi square plus, now you get 16 by pi square times sigma n equals 1 to infinity 1 by 2n minus 1 power 4. Okay, it's pi squared by 2, sorry, a naught squared by 2 should be pi squared by 2. Okay, so sigma n equals 1 to infinity 1 by 2n minus 1 power 4 will be pi square by 16 times, now 2 by 3 pi square minus pi square by 2, so that's again pi square will come out 2 by 3 minus half. Okay, that's fine. Okay, so this pi is fine. Okay, and that's equal to pi power 4. 2 by 3 minus half is 4 minus 3, 1 by 6, so pi power 4 by 96. Okay, now sigma n equals 1 to infinity 1 by 2n power 4 is 1 by 16 sigma n equals 1 to infinity 1 by n square, n power 4. Okay, and therefore zeta 4 equal to sigma 1 by n power 4 n equals 1 to infinity, which is equal to the odd ones and the even ones. So you have 1 by 16 zeta 4 plus pi power 4 by 96, and consequently 15 by 16. So 15 by 16 zeta 4 is equal to pi power 4 by 96, and therefore if you cancel it, so you get pi 4, I'm sorry, zeta 4 equal to pi power 4 by 90. Okay, so that is how you compute. In fact, all the even powers can be computed, all the even zeta values can be computed, and you know the Riemann zeta function is very important, and it is not known for the odd powers. We don't know very much. In fact, the big result is was proved sometime in the 1990s, that zeta 3 is an irrational number. So this is was proved, but we don't know anything about zeta n for n odd. Okay, the even ones can be all computed in using Fourier series in terms of what are called the Bernoulli numbers. Okay, so we'll continue the exercises again.